so this one will be about the solutions of practice problems. I have already posted one video where I have solved the first 9 problems in the practice problems document that I sent some time ago. And in this video, I will solve the rest. I do not have time to make individual videos for the last 2 classes, so I will really try to give you as much as of the explanations I can give you while solving these problems. So this video will both cover the numerical aspect or the mathematical aspect of problem solving as well as the physical aspect of problem solving. So you go to if you go to the home page, I should say, not home page, if you go to, home page and to, scroll down to this mechanics tab, mechanics unit, materials through test 2, and if you click on it, a document will open with some questions in it. The first 9 questions are solved already, as I have said, and the rest of it I will be solving right now. So we start with question number 10, and as you can see, it talks about a Stanley drinking cup that is placed in a box on the floor as shown below. So it's a multi-part question. This is the setup of the thing. You've got the ground on, and the box is sitting on the ground, and the Stanley cup is sitting on the box. Question number first is part A is list all the forces that are acting on the Stanley drinking cup. Don't forget to include the directions in which the forces act. Okay, so this is about um, how you understand like uh, the forces and the reaction to the forces, basically law of interaction. So I'm gonna go ahead and try to solve this problem. So the problem is that we have to list all the forces that are acting on the Stanley drinking cup. So imagine yourself if is sometimes it is easy to imagine you yourself being the object that we are discussing about. So imagine you are that Stanley cup. And you're sitting on that box, right? What do you feel? The only thing you feel on you is the reaction from the from the box. Okay, so that is the answer. It is kind of like it is a little tricky because it asks you to list all the forces, but there's just one on the Stanley drinking cup. So you've got the ground, you've got the box, and you've got the cup, right? That's your cup. So if you're that cup, the only force you are experiencing is the reaction from the box. Reaction from box. Okay. So that's the only force you're experiencing. And if you are curious, and I'll get to that in a second, this is reaction because of the action of the weight of Stanley Cup on the box. Okay, so there's always action and reaction pairs. So we're not talking about that just now, but just in case if you're wondering, that reaction is the reaction because of the weight of the Stanley Cup the Stanley Cup is exerting on the box. Okay, question number part number B of this question is list all the forces acting on the box. Okay, so if this is the box, now again, sometimes it is nice to imagine yourself as the object that is in discussion. So if this is the box, what are the forces acting on you? Okay, so if you're the box, first of all, like you when you were a Stanley Cup, the reaction that you were getting was from something that you were sitting on. So if you are the box now, you're sitting on the ground, so you will get the reaction from the ground, first of all. On the box. Okay, reaction from the ground on the box. And the second thing you feel is from the top, the weight exerted by the Stanley Cup on you. So from the top, the weight exerted by the Stanley Cup on you. So let's say that weight is like that, right? Weight of Stanley. So these are the two forces. If you're boxed, these are the two forces you experience. As I was solving this problem, I realized that questions C and D do not make sense. So I'm going to go ahead and scratch them off. I'll make the edit in the document that I have uploaded in Canvas as well. Um, these questions, the part C and D, they don't make sense in this scenario. So for question 10, there are only two questions, two parts of question 10, that is A and B. So that is just enough for this question. Next we see are these equations. First we've got average speed is equal to half times final speed plus initial speed. And the second equation is the modified version of that. It is when you let go of an object from rest of the object start, or the object starts from rest. The initial speed is 0. So if you plug that 0 in here, you get this formula. That's the updated formula. So whenever you let go of something, or whenever something starts from 0, the average speed is equal to half times the final speed. So this is like a just from a first glance, what I'm looking at is understanding graphs and looking at the curves in graphs, and to get information from the graph is what will you will be tested on. So acceleration, there's a little statement here. Acceleration is the rate of change of velocity, the change in velocity divided by how long it took to make the change. So acceleration is final speed minus initial speed divided by time interval. Similarly, if an object starts from rest, the initial speed is 0, so acceleration is final speed divided by time interval. The law of force and acceleration, the second law, is called is the second law. It is basically says that an unbalanced force will cause an object to acceleration, or in other words, when you have an equation, net force equals to mass times acceleration, where I can write that down as F equals ma. This F is actually net force. This is not just one force, two force, or any number of forces. This is the net force, right? And that is equal to mass times acceleration. So if you don't have any net force, this means 0 equals to ma. This means that there is no acceleration, right? But if F is not equal to 0, that means that there will be acceleration. And then when F is not equal to 0, that is what an unbalanced force is called, or we say there is some net force. So question 12 is, at some airports there is a subway that will take you from one terminal to the next. I know this is in Chicago. Um, to get to one terminal to the next, you go through like this and like subway, and then at some point you also go through this like under passage, and there's like tarmac on the top, and there's a travelator. There are a couple of travelators, and you're going through like this really nice light piece where there's like halogen lights or something. They look really nice. This happens like this is the first thing this came to my mind when I thought of this subway and transfer from terminal to terminal. Anyway, here's a graph that shows the position of the subway car as it goes from terminal A to terminal B. Okay, so terminal A to terminal B, as we can see, it takes 0 to 20, so it takes 20 seconds to get there, and the distance between the two terminals is 200 meters. Okay, that's the first thing we can get out of the graph, and that's what the problem says, a distance of 200 meters. Question number 1 is, what is the average velocity of the subway car during the first 6 seconds? First 6 seconds. Okay, we're talking about the average velocity for the first 6 seconds. Average velocity is the total distance traveled. Remember, like when you know the what is it? When you know the final speed and initial speed, then the average speed is this, right? this formula also works for velocity. Um, so it is average velocity can be known if the final velocity and initial velocity are known. But we don't know the final velocity and initial velocity. But what we know is in the first 6 seconds, how much was the distance traveled. So this is 1, 2, 3, 4, 5. That means 5 boxes. Like if what we see is that 5 boxes correspond to 10 seconds. That means each box is 2 seconds. Okay, so I'm talking about the first 6 seconds. So I'm just gonna see how much was the distance covered in the first 6 seconds. So that's 2, 4, 6, and the distance covered was this much, which corresponds to this right here. Right? First 6 seconds. So this is the distance covered. So from 0 to 100, I've got 1, 2, 3, 4, 5 boxes. That means each box corresponds to 20 meters. So that means that this distance is 20 meters. Okay. So for the first 6 seconds, the distance covered was 20 meters. So the average velocity average is time in downstairs 6 seconds and 20 upstairs, and then you've got meters per second because you're measuring the distance in meters and time in seconds. What is the final velocity of the subway car? Okay, so we're talking about the subway car velocity at this point right here at the end of the first 6 seconds. So final velocity, right? So just from this equation right here, you know that the average velocity is half of the final velocity. And I know I'm saying velocity and I'm reading, like I'm seeing speed and I'm reading velocity, but this is also true for velocity. So average velocity is half of the final velocity. Okay. So final velocity. So average velocity is equal to half of the final velocity. Remember, this is only true when the initial velocity is 0, which is true for this case because it tells us that the um, should say somewhere that it starts from rest, and it says it right here. Oh, but that was not for the question that we are discussing, right? Um, there's another correction then. It should say that the car starts from rest. Okay, so the car starts from rest. So that's why average velocity is half of the final velocity, and we're required to find the final velocity. The average velocity is 20 over 8 from this part is equal to half times final velocity. This means that final velocity is equal to 20 over 8 times 2. So the way you do it is you multiply both sides by 2. Okay, so if you multiply this side by 2, then this 2 will cancel the 2 downstairs, and then you will have an additional 2 multiplied by 20 over 8. So that means that this is equal to 20 over 4 meters per second. That's the final velocity. Now the C part is estimate the acceleration of the subway car during the first 6 seconds. Okay, so I'm going to use this formula. Acceleration is final speed divided by time interval. So here, as you can see in the discussion, they only give the formulas for like containing speeds and not velocity. The reason is that velocity contains the one more bit of information than speed. Velocity also tells you the direction. Here we just assume that like there's no direction change, so it was not as if the car starts from A, terminal A, goes to B, comes back to terminal A. right? So that's why we are able to interchangeably use speed and velocity, because the direction really doesn't really matter here. So that's something to keep in mind if you're getting confused with the speed and acceleration, speed and velocity in this problem. Part C is estimate the acceleration of the subway car during the first 6 seconds. Okay, so acceleration is equal to final speed, or I should say velocity, but doesn't really matter in this case, divided by time taken. So final velocity is 20 over 4 and time taken is 6, which is equal to 20 divided by 4 times 6, that is equal to 20 over 6 4 or 24, and the unit will be meter per second. The unit is meter over second. Over second is the reason is on the top you've got velocity, which has units of meter per second. At the bottom you have time, which has units of second. So when you do meters per second over second, you get meters per second, not over second, but meter per second square, because there are 2 seconds now at downstairs. So that is the answer, 20 over 24 meters per second square. Just want to say that you don't have to keep these numbers in fractions. I'm just doing it because I'm too lazy to grab my calculator or my phone to actually calculate those numbers. But these numbers are perfectly acceptable. Um, so don't worry about if you want to answer in decimal, you can actually use the calculators and find out these values in decimal. If you don't want to use that, it's perfectly fine. Remember, in these problems, units are really important. So if you write down something like 20 over 24 for the acceleration of the subway car in the exam, and then not write meter per second square, I might take half a point off or something. So this is really important that you write down the units correctly. Question number D is, what is the maximum velocity of the subway car during the time interval of 6 to 12 seconds when it was traveling with a constant velocity? Okay, so it says that between 6 to 12 it travels with constant velocity. So we should be able to see that between 6 to 12 seconds it is traveling in a straight line. Let's make sure that is the case. So that's 6 seconds. Every box is 2 seconds, so that's 10, then that's 12. Okay, so yeah, it makes sense that this is a straight line, and that's why it says that it was traveling with constant constant velocity. Okay, and what we are trying to figure out here is the maximum velocity of the subway car during the time interval 6 to 12 seconds when it was traveling with a constant velocity. This velocity is same as the final velocity of the subway car at 6 seconds. Because if you look at the graph here, uh, the velocity starts, like the velocity increases here, right? That's why you see that. And at this point, which is 6 seconds, the velocity does not change after that point, right? So whatever velocity is here is the velocity at 6 seconds, because from 6 seconds to 12 seconds, the velocity does not change. That means the answer to the question, what is the maximum velocity of the subway car during the time interval 6 to 12 seconds when it was traveling, is a constant velocity, is the velocity that it had when the time was 6 seconds. So at 6 seconds, the velocity it had was 20 over 4 meters per second. This is a good question because this kind of confuses you a little bit. Um, that's a very interesting question. What is the acceleration of the subway car during this time interval? So this question really tests your understanding of acceleration. Whenever there is acceleration, there is a change in velocity. That change can be such that the velocity is increasing or can be such that the velocity is decreasing. In this case, between 6 to 12 seconds, which this question is talking about, the velocity is constant, does not change. So if the velocity does not change, then the acceleration is zero. Okay. You can also see that mathematically from the formula of acceleration. Acceleration says final velocity, and I'm going to read that as velocity, not speed, or you can also use a speed if you want. But I just want to say one more time, because here we're only traveling in one direction, that information that you get from velocity is basically already known. So you're able to interchangeably use speed and velocity. So we're talking about why acceleration is zero. Acceleration will be zero when the final velocity is same as the initial velocity, and that's what we see. The velocity that it has here is the same velocity as 12 seconds. This is a straight line, okay? A straight line in distance time graph tells you that the velocity is constant. So that's why also the acceleration is zero. On to the next one. Question 13 is, if you dropped a ball from rest, water break. Question 13 is, if you dropped a ball from rest out of a window and it fell for 1 second, what would its final speed be just before it hits the ground? Okay, in the hint it says all freely falling objects accelerate at 10 meters per second squared. This is really important for you to know. An object in a free fall is like this. Pew! Or if you just chuck it upwards like that, this is all free fall. The acceleration is always 10 meters per second square and then 9.81 to be precise, but let's use 10 meters per second square here. This is also called small g. Do not get confused by this small g and the grams small g that we use. Okay, look at the units. If this was grams, the unit would be in grams, right? It would not be in meters per second square. So whenever you see meters per second square, then it is the acceleration. And whenever you see whenever you see they say that all falling objects are accelerated 10 meters per second square, they're talking about the small g, which is the gravity, the acceleration felt by every object that is around the earth and that is falling towards the earth. That's the acceleration. So we know the acceleration, okay? And we also know one more thing, and that is that it was dropped from rest. That means the initial velocity is zero. So let's do this thing. What are the given quantities? Velocity initial zero, okay? Time, it fell through 1 second. Final speed unknown, so unknown final speed. And we also know acceleration is equals to 10 meters per second square. Okay, so we have three things with us. We have initial velocity, we have got time it falls through, and we've got the acceleration, and we're supposed to find the final speed. Just so that we are consistent, I'm going to use velocity. Okay, or maybe I should do speed and speed. Again, you can interchangeably use velocity and speed in this case, because the direction is we know it is the downward direction, so we don't really care about, we already know what is the direction of that speed. So if I say velocity or if I say speed, where this ball is being dropped downward, it carries the same information. So I can just use speed here. Final speed is unknown. Okay, so we use this formula. So this formula right here. This formula connects acceleration with final speed, initial speed, and time interval. Okay, so that's a benefit of writing the stuff that you are known, that you're given or that you can infer from the question, and the stuff that you're supposed to find out, that is the unknown. So let's do that. Acceleration is equal to final speed minus initial speed divided by time, right? So acceleration is 10, final speed is what I need to find, and initial speed is 0 because you let go of this object from rest, and the time taken is 1 second. This means if you solve this, and I can actually do one more step for you, it's gonna be 10 final speed minus 0 is final speed, and divided by 1 is basically being divided, like you don't have to write divided by 1, or you can imagine multiplying both sides by 1 and 1. So the final speed is 10 meters per second. That's your answer. How high was the window? Okay, how high was the window? So we know the final speed. Let's do this. Let's do this. So we know everything we know here. Copy, paste. That's the given. And we also know final speed. That is 10 meters per second. And unknown is the height. So we're looking at the height it fell through. When it fell through for 1 second, the acceleration was of course 10, and the final speed was 10 meters per second. Okay, so what we can do is we can look. So when you if you knew average speed, you will say average speed is equal to final, sorry, average speed, not that one. Average speed is equal to distance over time, right? Keep that in mind. I'm going to erase this for a second so that I can have more space to work with. Right? So average speed is distance over time. Now average speed is also half of the final speed. Okay, and we have discussed why that is the case. So average speed is also half of the final speed. So average speed is equals to half of the final speed, and final speed is 10. That means average speed is 5 meters per second. Okay, so I'm going to use that 5 meter per second in this formula. Average speed is 5 meters per second. On the right you've got distance, and at the bottom you've got time, which is 1 second. This gives you distance to be equal to 5 meters. All right, so it's a good problem because it just does not test you um, on the formula of average speed, which is distance over time. But mind you, average speed also has one more formula where it is, sorry, where it is half of final speed plus initial speed, and this is also the same formula when initial speed is 0. So that's the first formula, right? And it also has a second formula, which is just distance over time. So it tests you on that understanding where you know these two formulas. It also tests you on this, where you can tell that the average speed that you have found out, sorry, the final speed that you have found out, if you multiply that by half, you get the average speed. So once you do that calculation, you have to use again this formula by plugging it the value that you get for average speed here, so that you can calculate the distance to be equal to 5 meters. How many more? Alright, last one. Question 14. Question 14 is a box of mass 0.5 kilograms at rest on a horizontal surface as shown below. If the box is pulled on both sides by the two forces as shown below. Part A. What is the net force acting on the box? Well, if a force of 2 Newton is to the right and another force of 2 Newton is to the left, then net force is 0, right? Is 0. Sometimes some people like to think about something where they say, okay, whatever is towards the right is going to be positive, and whatever is towards the left will be negative, right? So F2 is positive 2 newtons, F1 is negative 2 newton, and F net is F1 plus F2, which is minus 2 plus 2 equals to 0, right? So if you like to think that way, you can think that way as well. By just looking at it, you can also say that the net force is 0, okay? Now, at this point, I should tell you, whenever net force is 0, there are two possibilities. The possibilities are either there is constant velocity of the object or there is no velocity at all. Okay, remind, just keep this in mind always. This is what net force equals to 0 means, that there is no acceleration. Therefore, if there is no acceleration, the velocity is not changing. That's the first case, constant velocity. The second is basically it is not moving at all, because when it is not moving at all, it means that it is moving with constant velocity being 0. Okay, so remember, net force means two things. What does the law of force and acceleration say about the motion of the box? Okay, so law of force and acceleration, because basically this question is talking about the second law, which is this equation: F net is equal to mass times acceleration. Okay, so what does this tell you about the motion? Okay, well, clearly we have discussed that net force equals to 0 means constant velocity or no motion, like no velocity at all. But let's look at that from the equation this time. So we know that F net is equal to 0, right? So we've got 0 equals mass times acceleration for small a. I mean, small a for acceleration. Divide both sides by mass, so you get 0 equals to a. So you get acceleration is 0. If acceleration is 0, acceleration means change of velocity. It can be increasing, it can be decreasing, but it means change of velocity. So if this acceleration is 0, that means velocity is constant. Okay, velocity is constant. That's first thing that we know about this. Either it is moving with constant velocity, and the second thing we know about this is has zero velocity or at rest. Okay, so two cases when the net force is 0: constant velocity or zero velocity. So that's what we know about the motion of the block box. So this is a question where if you answered, let's say, only constant velocity, I might take a half point off, because you are missing the second case entirely. If you answer zero velocity or rest, I might take half a point off or something. I might take even 1 point off. It doesn't really, like, I don't have a rule, but I'll take something off because it will be an incomplete answer. Alright, C is the variation of the problem where it says if the force F2, and F2 is the force to the right, is changed to 5 newtons, what will be the net force on the box? Which direction will the box move? Alright, let's see. So you've got box here, and then this is now 5 newton and this is now 2 newton. So just from the intuition, imagine this is that box. To the right, I should say this is the right. Oh, doesn't really matter. Let's say the 5 Newton force is this way, right? And 2 Newton force is this way. So we know there's a net force. So if there is a net force, then there will be acceleration. But the object will move towards where the force is more. Just makes sense, right? If 5 Newton is here, if someone really strong is pulling this ball to the right, and I, being very weak person, is pulling it to the left, I will lose and the ball will start to move to the right, right? That's the whole point. So we know that it will move to wherever 5 Newton is, which is to the right in this case, right? Let's see that mathematically. So we again use this F equals to ma, and let's say this is positive and this is negative. So F is basically F net. So you've got F2 to be positive because it is to the right, plus 5 newtons. F1 to be negative because it is to the left, so that is minus 2 n newtons, equals to mass times acceleration. This gives you this number to be equal to 3 equals to mass times acceleration, and this gives you, if you divide both sides by m, acceleration is 3 over m, and this is positive. Okay, this is positive acceleration. That means it is moving to the right wherever the larger force is. So that's the direction of the box. Part D, penultimate part, is what does the law of force and acceleration say about the motion of the box? Well, in this case, the net acceleration is non-zero. Sorry, net force is non-zero. That means the box is moving with acceleration equals to 3 over the mass of the box. It does not tell us what is the mass of the box. If it had told us what is the mass of the box, we can actually calculate the number, but it doesn't really matter. All it matters is that it is non-zero. What is the acceleration of the box? Well, oh, okay, we were far ahead. We actually calculate the acceleration in that part. The acceleration is equal to 3 over m. So this video is definitely long, but I promise you, if you go through this video, try to understand how I'm able to use different information given in the problems to figure out what I'm supposed to find in the problem, and really go through all that process, try to work out the problems yourself. It will be really, really helpful. Okay, so that's pretty much it.